So Christoph told me that the last lecture will be half an hour shorter. So anytime there's a point in the argument where the argument is messy or I don't want to do it, I'll say that was going to go in that last half hour. Okay. Okay, so I think it's past, so I'll start. So quiet at the front there. Oh, that's okay then. So last time we said we have this sort of H was sort of edge empirical distributions, the fraction of edges that are blue on one side and red on the other, and we had this sort of function of H, and we said that the expected partition function was you maximize this over H, and it's basically e to the n times phi of H. And at the end, I claim that the H's that maximize this have a nice form. So if you have a maximizer, and actually not just a maximizer, any stationary point will satisfy these relations, then there exists an M. M is a fixed point of the BP equations, and then our maximizing H will be given by essential, or will be the edge empirical distribution on the corresponding translation invariant Gibbs measure that corresponds to this BP fixed point. And phi of H will be the same formula that we saw for in the uniqueness regime. So where here sort of by phi vertex of M, I mean sort of if you have a vertex V and the incoming messages are all M, and you look at change of the log partition function when you delete vertex V, then that's phi vertex of M, and phi edge of M is the same thing where you delete an edge. And this was the formula. So we said before, if there's a unique Gibbs measure, then there's a single BP fixed point M, and the limit of 1 over n log of the partition function is given by this formula. And the expected partition function is also of that form. So I'm going to prove this, well, there's a couple of proofs. There's a proof in the notes which just does it by calculus. You just sort of differentiate phi, do some algebraic manipulations, and in a not very illuminating way, you get that H must sort of satisfy these equations. I'm going to give a more probabilistic proof, but it will be limited to the case where H is a global maximizer of this function. And I'm not going to prove this last part because it's sort of just an algebraic identity that you can check. Okay. So the way I want to do this is I'll let HM be BP M of X, psi of XY, M of Y. So it's not this formula. I've got BP of M, and this is like d minus 1 times. But when I write BP of M, I'll mean sort of the d minus 1 times version of it. And what I claim is that, for all delta, I can find an M such that H star minus HM is less than or equal to delta. And maybe this is an m delta. And then, okay, if I could do this, then for any, I could take sort of some convergent subsequences of the m deltas and find one where h star equals hm. And h star has the property that any h of this form has to be one where h of xy equals h of yx. It's the empirical distribution of edges. So every time you have an edge that's red on one side and blue on the other, it's also blue on one side and red on the other. So, so if h of xy equals h of yx, then it means that if I swap the BP over to the other side, I get the same distribution. But and so that this can only hold if m equals BP of m. Okay, so that will be the plan. And the way I'm going to do this is a sort of resampling argument. So I will pick sort of G and sigma according to, it's called the planted model. And this will mean I'll write a probability distribution for a paired G and sigma. And the normalizing, well, so it will just be proportional to the weight of sigma. So U and V, sigma V, sigma V. But so I mean this was normally what we write if we sort of just fix G and then take a random sigma, but I'm also letting, you know, this probability distribution be over G and sigma. So so it's taking the random pair. Okay, and so the normalizing constant is the 1 over the expected partition function times the number of matchings of dn, which is the same as the number of graphs. So it's like what you get if you sum this over all the possible graphs. Okay. And so now, and let me write H sigma is the empirical distribution over, you know, this is the edge empirical distribution. And I claim that, okay, the probability that H sigma equals H star is greater than or equal to some, like 1 over some polynomial. And this is basically because the probability of seeing a particular empirical distribution under this this measure is basically just proportional to e to the n phi of h. That was the calculation we did last time. So and because h star is a maximizer of that, then this is sort of the highest probability, and but there could be multiple maximizers, but the total number of choices of h is just polynomial in n. Okay, so it's maybe rare, but not too rare. I'm also forgetting about rounding, so this should probably have a plus order 1 over n here. Okay. Yeah. Okay. And let me call this event A. Okay. And now, so now I want to take the take my pair, G and sigma, and kind of delete some vertices and resample them and see what happens. So I'll let W plus be 2 epsilon n random vertices. Now I want them to be not next to each other, so I'll sort of let W be W plus minus sort of any vertices that in W plus that's next to another one in W plus. Okay, and at least if epsilon is small, most vertices that I pick won't be next to any other ones. So I'll get this set W is greater than or equal to, let's say, epsilon n, except with probability exponentially small. Okay, so these W are just sort of random vertices, and they're not, and none of them are next to each other. They could be at distance 2, perhaps, but that won't matter. And so what I want to do is, so I take W. So this is drawn in a sort of a 3 coloring. So take W, delete those vertices. So I still have, so I have all the vertices. So all of the graph except W remains the same. All of the colors in it remains the same. And then I want to resample W according to the planted model distribution. So add in, add back in, W number of vertices and connect them up to according to a random matching with probabilities according to these weights. Okay, and I want to see sort of what happens to this distribution. And so one point I want to make is that the starting point and the end point are exchangeable. I sort of started with some distribution, I did some resampling, and according to so it's like a sort of like an update of the Glauber dynamics. Okay. So the distribution I have at the end will be the same as the distribution I have at the beginning. Now I want to sort of count what the empirical distribution looks like in the neighborhood of W. So I'll let L sigma of xy. We'll count the sort of fraction of edges starting at W. So WV, so that W is in W, sigma W equals X, and sigma V equals Y. Okay, so it's looking at the empirical distribution around a neighborhood of W. And I want to claim or define 3 events. One is that L sigma is close to H sigma. A2 will be that L sigma minus L will be close to L sigma prime. And that L sigma prime will be, or actually, there exists an M such that L sigma prime minus HM is also small. So if all of these events hold, then it will say that H sigma is close to HM, which is, and if if h sigma equals h, then that will mean that h sigma equals h star, then h star will be close to some hn. Yeah. Oh, it's a d times w. So this is just, yeah. So it's just over the d times the size of w number of edges there. Good. Any questions about that? So what I want to claim is that all of these AI have probability at least 1 minus e to the minus a constant times n. So they're all very likely to hold. The first one is maybe the most, doesn't require much at all. It's because essentially these W were chosen almost at random. So the empirical distribution around their neighborhoods should look like the empirical distribution on the whole graph, just because the sample mean is close to the population mean in a distribution. So we picked some random vertices, looked at their random neighborhoods, and that was close to the distribution in the whole graph. And so the Zuma-Hofting inequality will say that these should be close, except with exponentially small probability. So that's just sampling. Doesn't depend on anything that we've done so far. So now I want to sort of create, in order to, I'll do the third one next, by sort of giving a recipe of how we could sort of generate this resampling scheme. So So we have these boundary vertices. And I could think about it as saying I have W d stars. So I'll call these vertices U. And I want to choose spins on U. So according to, so choose a coloring. So maybe this is green. This is blue. And then and the distribution on this coloring that I want will be, so I'll call this configuration sigma star, and I want the probability of sigma star to be product of U and V So I have sort of weights on each of the edges, but I'm only putting a weight on the root of the D stars, not on the children. And I claim that if I take this distribution and then for each of these, so take each of the colors on the leaves, I take a perfect matching, so match red ones up with red ones, blue ones up with blue ones, and green ones up with green ones, then this is the right distribution to resample with here. I'll get a, But in order for this matching to work, I need the same number of blue, red, and green here as blue, red, and green here. So I need to condition on, okay, of course I forgot to, so I'll write L bar of sigma equals sum over x L sigma of xy. So this is just the empirical distribution on these leaves on the boundary of W. So I need to condition that L bar of sigma star is equal to L bar of sigma. Okay. Any questions about that? Okay. And then I want to check that when I do this operation, I get a distribution back, and well, it looks close to some HM. Okay. So the difficult thing here is that we're conditioning on saying I want a certain number of red, blue, and green on the leaves. And that could be an exponentially rare event. So we want to tilt the distribution to make it a more common event. So let me change sort of this distribution, and that's not good.
Maybe the
is that? Yeah. Is that clearer? Okay. So I'll product of V in delta U of MV. So I'm adding, essentially I'm adding some extra weights on the leaves here to sort of push the distribution to make this condition more likely. And how do I want to pick M? Well, of course, with this distribution, sort of my graph is just these disconnected D stars. Then unconditionally, they're just independent. So I can just sort of do the calculation within one of these fixed trees. And if I add weights M sort of on each of these, then it's the same as sort of doing belief propagation calculation, where I have a sort of boundary condition message M. And so if we took these upgoing messages M, then the downgoing message would be BP of M. And if I look at the distribution now on say an edge, it will just be given by H of M. So so if I want to look at the expected value of L sigma star under this M measure, it will be given by H of M. Okay, and so what I'll do is pick M such that expected value under M of L sigma star bar is equal to L sigma bar. So I claim that we can always find such an M, and this is essentially just saying that there's some way of reweighting the distribution to change its mean to be equal to some particular value. If you were doing like Cramer's theorem in large deviations, you want to ask what's the probability that a sum of n IID random variables has an average that's some value, you want to sort of tilt the distribution to make each of them have expected value, that value. And picking this m is done in exactly that way. Okay, and so as long as this distribution is not too crazy, and it won't, and you can show that it, because of the way we constructed things, it won't be, you can always find an m that does this. Okay, and so if we've done that, we can say that, well, the probability that L of sigma prime minus hm is, say, greater than delta over 4 is the same as the probability that L of sigma star minus hm is bigger than delta over 4. Okay, sorry. All of this should have been conditional on well, yeah, I mean, conditional on what we see from the rest of the graph, essentially the boundary condition that we have before resampling. This is the same as probability that L sigma star minus hm is greater than delta over 4 given L sigma star bar is equal to L sigma bar. And I claim that this is the same as the probability if I do the Emery weighted version. And the reason for that is, okay, we're adding this sort of reweighting term on each of the sort of boundary vertices here. But the product of this sort of reweighting terms depends on how many, reds and blues and greens you have in the boundary condition. So when we do this conditioning, when we're conditioning on the empirical distribution on the boundary, the reweighting we do going from P to PM is the same for every configuration. So we don't change the distribution at all. So these have the same probability. And then, so everything's an identity up to this point. And then sigma star, this is under the M measure. So I can just write it as the ratio of these probabilities. And what can we say about these? Well, the numerator is, the numerator, this would be a large deviation event because we said under the P measure, the mean of L sigma star was hm. So this would be e to the minus a constant times n. And now the denominator, well, the mean of L sigma star bar is L sigma bar. That was, we chose M specifically so that would be the case. So this event is a local central limit theorem type event. So it will have probability like n to the minus a constant. So this is, the denominator is small, but it's much bigger than the numerator. So overall, this is less than or equal to e to the minus a constant times it. So when we do this resampling, the scheme is really like pick the right message to put on the boundary, M, sample according to trees with this boundary condition, and then match the vertices. Identify the leaves of these D stars with the boundary, and then you get G prime and sigma prime. Yeah.
Delta is, so it's like we began with for all the elements, right? Then we go to a large deviation event. So
yeah.
I suppose that delta should be of the same order of expectation.
Yeah, so
otherwise I should have seen it on the right hand side of the inequality, or
there will be the constant in the large deviation will be a function of delta.
okay. So
Yeah.
okay.
Yeah, but that's okay because we're comparing it with some polynomials. So when n is big enough, the numerator will be much smaller than the denominator. Okay, so that's showing that A3 has probability close to 1. And the last one is that saying that L sigma and L sigma prime have close to the same distribution. Now I constructed them by starting off with G sigma, deleting W, and then resampling. But I could have also constructed this pair by sort of somehow constructing this distribution first and then resampling twice to get these two. But so then the same argument as we just did should say that both of these should be concentrated around this distribution HM that we just constructed. And so by the triangle inequality, we should get that L sigma and L sigma prime are close to each other as well. Any questions about any of those steps? Okay, so if the event A that H sigma equals H star holds, and A1 and A2 and A3 all hold, and this has probability at least n to the minus a constant minus 3 e to the minus constant times n, so it's greater than 0, then by, I guess, the triangle inequality, H star minus HM will be less than or equal to delta, and that's what we needed. And then by taking an appropriate limit, we can find an m such that H star equals HM, and by the symmetry of H, it must satisfy the m must satisfy the BP equations. Okay, good. Any questions about this? Yeah.
So, which part of this proof do you need the fact that you don't have like two replicas?
Nowhere. So I mean, because we're just calculating an expectation, so
I guess we need it at some point.
no. I mean, if we were in the replica symmetry regime, that would sort of just say that the expected value isn't really telling us much about what's happening, but we could still calculate it. So it may be that some of the time this is not a very relevant theorem, but it will still be, it's true for any choice of spin system and potentials, whether or not it's replica symmetric or replica symmetry breaking. But does that make sense? Or okay, good. Any other questions? Okay. So let me just. Maybe I shouldn't use that. Yes, because the planted model I know something about. Okay. So I mean, if I, yeah. So okay, I guess where it's important is that this resampling is, the way I did it is sort of stationary with respect to the planted model. So it wouldn't, I couldn't necessarily say that about another distribution. And under the planted model, I know that, I mean, the planted model is just very closely connected to taking expectations. When I, if I take the standard distribution where I take a random graph and given that the configuration on it, then different random graphs have different partition functions. So one couldn't do the calculation for resampling there. Okay, so let me do a couple of very simple examples. One is so coloring. So K coloring. So M of X into So if I want to find the fixed point of this, well, the bigger the value of M of X, the smaller the value you get on the right-hand side. So the only solution you can have. X prime. The only solution you can have is M identical. All of the M of X equals, so 1 over K. And so if you substitute that in, you get, using this formula, it would be log of K 1 minus 1 over K d minus 1 minus d over 2. So that would give, so the expected number of colorings is e to the n times this. If I was looking at independent sets, then the formula would be m of 1 equals d minus 1. One. The right-hand side is decreasing in M1, so there can only be one solution again. M star. And the solution for M1 will be approximately log d over d, at least if d is big. Okay. So that would give it, so then we could plug this into and get the exponential growth rate of the number of independent sets. Okay, but what if I'm interested in not just counting uniformly the number of independent sets? I want independent sets of a particular size. So I guess this analysis is saying that most independent sets have density about log d over d. But some of them will be smaller than that and some will be bigger. So what if I want to count the number of independent sets of, let's say, size alpha times n, or at least work out the expected number of them. I mean, this isn't you don't need this theorem to be able to do that, but I want to sort of, well, I'm going in a particular direction with this. So now, I mean, how does this fit in with the maximization when we're adding in some extra constraint? I only want to look at one particular set of solutions. So we have, I guess, the sort of simplex of empirical distributions, and this is our global maxima phi of h star. But I'm interested in just empirical distributions on some different hyperplane within this simplex. So to get the sort of exponential growth rate, I want to maximize phi of h over h, but subject to the constraint, say, h bar of 1 equals alpha. So the density of 1s is equal to alpha. Okay. So now we're talking about constrained optimization problems. So how do you do a constrained optimization problem? Sorry? Yes, Lagrange multiplier. At least that's the only way I know how to do it. So we want to find the maximizer here. So we would sort of introduce. So maximizers should be of the form. I'm probably getting too low here. Or phi tilde of h is phi of h plus, say, theta of h bar of 1. Okay, so so where this will be our Lagrange multiplier, and okay, and so what happens when we add in a term like this? Well, suppose I go back to this formula here, and I want to add in theta times h1. Well, I could just sort of, so plus theta times h1. I could incorporate this term into this one just by changing psi. So I could write psi bar of 1 as equal to psi of 1, which was just 1, times e to the theta. And then for this, modified spin system, my phi tilde would be the function for that. So just doing, well, and okay, and what would that new spin system be? Well, let's. If I let, let's say, lambda equal e to the theta, then it will just be probability of sigma equals psi of v, sigma v. So this is the hardcore model, and then I introduce the new weight, and it will just be lambda to the sigma u. And this is just the hardcore model. So we've just gone from the hardcore model with lambda equals 1 to the hardcore model with fugacity lambda. So if I want to do this optimization for, you know, densities of independent sets other than the maximal one, then I should just add in this fugacity term, sort of tune the model to have, say, a higher or lower density of ones, and look for BP fixed points of that equation. So now we would be solving the equation m equals lambda 1 minus m d minus 1. D minus 1. And, well, if you want to, so the values that of the densities that you can get are going to be somewhere between 0 times this and 2 times this. So, right, alpha equals beta log d over d. And so if m is a fixed point, then alpha will be equal to lambda to the 1 minus m to the d. But this is very close to m as well, because the only difference is here we had d minus 1, the BP equations, and for calculating the marginal, you have at a vertex of degree d, you have a power of d instead. But 1 minus m is going to be very close to 1, so this won't matter much. And so then we can, you know, plug this into the formula, maximum over h of star. There's again just a single BP fixed point. So it's phi vertex m, edge m, and we'll get squared. This first term will be, well, this is close to alpha, so it will be about beta log d over d. And then this is m squared is sort of small, so it will be like plus d over 2 times m squared. So d over 2 times beta squared log squared d over d squared. So these cancel out. This has a log squared, so this first term is kind of negligible. So that's that gives us the exponential, you know, the free energy for this spin system. But we also, if we want, let's say, limit as n goes to infinity, log 1 over n, log of the number of independent sets of size alpha n. We want it will be this quantity, sort of max over h of phi tilde of h. But we've also got to, I mean, we've added in this extra weighting, so we've got to subtract that off. And let me just, yeah, so so I should subtract off alpha times log of lambda. So what should lambda be? Yeah, so so if I rearrange, okay, so the denominator here is about 1. So if I rearrange it, lambda is approximately alpha times 1 minus m to the minus d, which is beta log d over d, times 1 minus beta log d over d to the minus d, which I really should write this out more carefully. So, okay, beta log d over d e to the minus, or e to the beta log d. So this is just d to the beta. So beta log d times d to the beta minus 1. Okay, and but then we take log of this, and so the main term we'll get is beta minus 1. So log of lambda equals beta minus 1 times log of d, and so if we plug that all in, we get log squared over d times 1/2 times beta times 2 minus beta. And so, okay, you see it's maximized when beta equals 1, as we expected. So the most likely ones are log d over d. And it tends to 0 both when beta goes to 0. I mean, you don't expect any independent sets of size less than 0. But also at 2. So in expectation, the maximal size independent sets that we expect to see are about 2 times log d over d. Okay, but this is all still just expectations. What if yeah, not much time left. Okay, so if we want to if we want to show that there are, say, independent sets, we want to do the second moment method. So we want to compute expected value of z squared. So we can think of z squared as also a partition function. So I'll write the spins will be a pair of configuration, a pair of colors for each vertex, because z squared is nothing but just the number of pairs of configurations and their weights, and so psi of let's say I'll write the psi squared for meaning the pair model. prime equal to psi of xy, psi of x prime y prime, and psi bar 2 of x prime will be psi bar of x, psi bar of x prime. So this is a valid spin system. We can compute its expected partition function, and it will be the same as the expected value of z squared. We can also write down BP equations for it. And if M is a BP fixed point for our original spin system, then sort of M squared of xx prime equals, then the sort of product one BP message will be a BP fixed point in this new pair BP model. And if you do the calculation, phi of M2 is just 2 times, okay, that actually, if H is the corresponding, I guess I'm supposed to write it like this. If H is the corresponding empirical distribution to M, then you just double the value of phi. And so if M corresponded to the global maximizer that gives us the optimal value of phi in the original spin system, then we'd like to hope that this sort of product of independent ones also gives us the maximizer in that case, in the pair model. And sometimes it will and sometimes it won't. So if it does, we started at 2:30, right? Oh, so I don't need to stop in 3 minutes then. I was like, I am so far behind.
You have the last hour, half hour.
So, okay, I can calm down a little bit. Okay, good. Okay, so we want to. Actually, before okay, so I'm going to say something about the second moment, but before that, actually, let me just say one thing about the original theorem. If I add in one more condition, which is I want sort of some property about how BP of M behaves in the neighborhood of the maximizer. So suppose M star is the maximizer, and I want that M minus BP of M. So if okay, so yeah. Yeah.
Here, when you tensorize, how can we view it in the level of measures? Because I mean, the measure with respect to m and the measure with respect to m
So
are related.
I mean, like the way I would think about it is just that you have two different. So you know, this spin system is like two copies of your original spin system, and when m factorizes, it means that the two copies are basically independent of each other, or that at least at the level of empirical distributions. So you should sort of the first copy doesn't affect the second copy. So if we looked at this, I mean, if I take a sort of set of BP equations or like a BP fixed point on the infinite tree, if they factorize like this, it means that the two copies we get are independent of each other. And that's going to be the case that we want for the second moment method to work. I'm not sure if that... Okay. Okay, so the condition that I want is that if I pick, so let's say m star is the BP fixed point, and I pick some m close to it, then m minus BP of m is not too small. It's sort of, it's at least some small constant times m minus m star. And this is the case in the colorings and independent sets and sort of all of the examples that I can think of that we've talked about, except I think for the easing model at the critical temperature, where this would be sort of m minus bm would start becoming would be, I think, like quadratically small or something like that. Yeah.
Just to confirm that, so in this factorized case,
yeah.
Fixed point is basically like any combination of two fixed points in single.
So I mean, a message m that factorizes like this will be like two independent ones, but we will see that we sometimes get BP fixed points which don't factorize like this. So you could imagine that most of the time the first copy is very close to the second copy, and so this won't be a BP fixed point for the models that we're thinking about, but in other cases it could be just mx times the indicator that x equals x prime could potentially be a BP fixed point. That won't be the case if the system is permissive, but it sort of corresponds. But you could imagine a perturbation of this, where most of the time, the messages are identical on the two copies, but sometime, but occasionally they're different. And yeah, so we'll see sort of examples of that as we go along. Any other questions? Okay. So if you know this, it tells you something about how phi behaves in a neighborhood of its maximizer, and essentially that phi of h minus phi of h star be greater than or equal to a constant time. So you'll get sort of quadratic decay around the maximizer. And the reason why it's nice to have a have a statement like this is that it's usually easier to check things about the BP fixed point than it is to check things about the underlying high dimensional function phi. So this is, and you know, usually this one holds. And so if we have this, we have this sort of quadratic decay around the maximizer. And then, okay, so we imagine in this, so space of empirical distributions, H star is here. If I draw a ball of radius sort of 1 on root n around it, then the values of phi in this ball will be sort of about of the same order, but as you go further away from that, then they'll sort of decay like a Gaussian around it. And so when we sort of have to sum up over all the empirical distributions of sort of this scale, and there are polynomially many of them. But it turns out that the polynomial number of them sort of fortunately matches all of the polynomial factors that you picked up every time you did Stirling's formula along the way to get to construct phi. So if you have these conditions, then expected value of z is equal to a constant plus the low of 1 times e to the n phi of h star. If h star is the unique maximizer, and it satisfies this property. Okay, so if your spin system and unique, well, okay, so let's say suppose both phi and the pair model 1 have a unique maximizer, and they both satisfy this one. Then you get the expected value of z squared over z squared converges to some constant. And so in that case, well, at least if it's permissive, well, at least with a positive probability, z will be close to its expected value. And if it's permissive, then 1 over n log z will be close to phi of h star with probability tending to 1. If you want to say something with probability tending to 1 in general, there are a couple of things to do. The most sort of formulaic is to sort of account for this constant here in terms of the effects of the small cycles. And there's a method called the small graph conditioning theorem where that essentially gives you a recipe for how to check that once I account for the variance that's caused by the small cycles of the graph, then z is concentrated. And then under that hypothesis, z over expected value of z would converge to some, in distribution, to some random variable w, and w will be positive almost surely.
Sorry, can I ask you again?
Yeah.
I think that I do not understood very well your answer. I was thinking that if m is equal to dt of m, it gives rise to a Gibbs measure.
Yes.
And the other gives rise, when it's a closed over, it gives rise to another Gibbs measure. No?
Yes. So when.
The question is about how they are related, these two measures.
Okay. Yeah. So the Gibbs measure corresponding to z is just a Gibbs measure on the tree. The Gibbs measure associated with this sort of pair model is a Gibbs measure on the tree where sort of at every spin you have like a pair of colors. So, and its neighbors, something like. And if you look at the first, so each vertex gets a pair of spins or colors. And so in this case, for 3 coloring, it means, the first one has to be different from the first one and its neighbor. The second one has to be different from the second one and its neighbor. But there's no relationship between the first one here and the second one of its neighbor. So it's just sort of as though so if I just look at the first one for each of them, then that's a spin system. And if I just look at the second one, then that's also a spin system. So it's like I just took 2 copies of the one spin system. And that's because, and why is it like that? Well, z squared is like the sum over sigma and sigma prime of the weight of sigma and times the weight of sigma prime. We're just sort of counting over pairs of them. And one way of encoding pairs is just to say, well, at each vertex I have a pair. Yeah, but I could get Gibbs measures where the choices at each of these vertices are not independent of each other. Yeah, and that will be closely related to the phenomena of clustering that we get, at least when the degree is large. So, I still haven't run out of time. Okay. Yeah. Also, when we have this property, let me tell you a couple of other things. If we look at the planted model, I'll call this P tilde. This, remember, we picked the graph and the configuration together. Then this is contiguous with respect to the original model. So if under the planted model, if I ask what's the probability of getting a particular graph G, well, it will be the probability of getting that graph G under the regular model, which is just the uniform distribution over graphs, times the partition function for the graph G divided by the expected value. But we've basically said that these ZGs are, of the same order as the expected value. So the sort of Radon-Nikodym derivative between these 2 measures is basically order 1. So if AN is a sequence of events, and probability of AN goes to 0 under the planted model, then the same is true under the original one. Okay, and quite often things are easier to sort of establish under the planted model. So let me give you an example of let's say local weak convergence. So we talked when we talked about random graphs, we talked about local weak convergence of graphs. But now I want sort of local weak convergence of a pair of the graph and a configuration on it. So, and I want to say that this converges to, in a sense of local weak convergence, to a tree and some measure mu on the tree. And by this I mean, okay, the probability that, so if U is a random vertex, the ball around U of radius r equals the tree of depth r, and sigma of the ball radius U around r is equal to x, that this should converge to, well, this one is just going to happen with, we want it always to be equal to the tree, and so I just want this to converge to mu of x. So that when I pick a random vertex, I take some, let's say, finite set A. I look at what the distribution, the probability of seeing some particular configuration here. I want this to converge to like the same XA under the limiting measure mu. And so the theorem is that under the planted model, we have local weak convergence to a tree and mu with m star, the maximizing BP message. So if m is the corresponds to the maximizing or the fixed point of the BP equations that maximizes phi, then this will be the local weak limit. So that's saying that we take our graph according to the planted model, pick a random vertex, look at its local neighborhood up to depth r. We'll see a tree, a deregular tree of depth r, and the spin system here will be mu of m star. And the reason is basically it just follows from the construction that we had of a particular. So if I have HM is the corresponding empirical distribution, then the recipe was sort of, okay, color vertices according to H bar, and then the neighbors according to, so let's say this one is X, then the ones that it's going to be connected to as neighbors will be proportional to H of Yx divided by H bar of X. And then these will be connected up with neighbors according to those probabilities. And then you just sort of explore the depth R neighborhood of this tree according to the way you constructed the graph. So you colored vertices with probability H bar, colored edges according to these sorts of probabilities. And if you do that, then when you sort of explore the tree down some ray, it will just be a Markov chain with these sort of transition probabilities. And that's exactly the Gibbs measure associated to M. Yeah.
Sorry, I don't
Oh, let's say M star is just the BP fixed point. And the one such that that corresponds to H star, the max equals H of M star, and H star is the, or phi of H star equals max of phi of H. So it's just the, so there'll be some maximizing H star. It's given by some BP message, or BP fixed point M star, and sort of this H star tells us what the empirical distribution should look like on the graph, and then the configuration model tells us how to build those configurations. And then if we take that construction, pick a random starting point, and sort of explore what its neighbors are and what its neighbors' neighbors are and so on, then as you go on a path in this graph, it will look like sort of a Markov chain with transition probabilities given by something like this. And that's exactly the gives you exact, and that's also the case for the corresponding Gibbs measure on the tree. Yeah, so that implies local weak convergence. If I picked you know, a bunch of like a set say a large number of different vertices and looked at the local neighborhood of all of them, it would be like approximately independent samples according to that distribution, and so it would be concentrated around that. So for a given configuration or a given pair G sigma, most of the time the empirical distribution of local neighborhoods is concentrated around you know, this mu of M star, and so that's an event that's happening with probability tending to 1, and it's a bit stronger than this. This local weak convergence, you're sort of averaging over, you know, also averaging over G and sigma and not just this random point U. But by sampling different U's, you can say that even when you condition on G and sigma, you still have this sort of convergence. So it's an event that happens with probability tending to 1. So the contiguity says that the same thing will happen under these hypotheses. The same thing will happen under the regular model as well. So you get sort of local weak convergence. Yeah.
It seems quite strong that local weak convergence carries through from the graph to the planned model.
Mm.
How general does this hold for graphs?
What other sorts of graphs do you have in mind?
A different configuration model?
Yeah, so I mean, for the planted model, you should sort of generally have this kind of behavior. Then whether you can sort of transfer that to the unplanted original model is sort of more of the question, but yeah, but I mean, yeah. So, and I guess I should say that, you know, as we get very close to, say, the colorability threshold, this is going to stop being, this local weak convergence is going to stop being true. So it really does depend on knowing this sort of contiguity. It would still be true for the planted model, but not be true for the original one. So yeah. Okay. So okay, so the last thing I want to say today is you know, eventually we're going to have to actually do the second moment to be able to check this condition. What can, you know, what happens when we do that? Well, I keep switching between different models, and basically my algorithm is to choose whatever the easiest one to explain a particular point. So I'm going to switch to the k-NAE-SAT one. Remember, this is sort of k-SAT where we ask that both x and its negation hold. And we'll condition on there being m clauses, and m equals alpha times n. So the expected value of z is, well, there's 2 to the n possible ways to assign the variables, and each clause independently has probability 1 minus 2 to the minus k minus 1, probability of being satisfied. So we get this. So, and m is alpha times n. So if I let alpha be log 2 over log 2 minus 1, I'll call this alpha 1, which is about 2 to the k minus 1 log 2. This is the point at which, I guess, for this alpha 1, the expected value will be 1 exactly. Okay. I mean, it would be nice if this was the satisfiability threshold, although there wouldn't have been much point for you coming to a series of 8 lectures if this were the end of the story. So what happens when we compute expected value of z? Well, so now we're summing over x and x prime, probability that x and x prime is satisfied. And between x and x prime, the only thing that really matters is how many variables they agree on and how many variables they disagree on. So I'll let gamma be the distance between x and x prime, maybe gamma times n. So you could write this as 2 to the n, sum over gamma, n choose gamma n, and then the probability that x and x prime are both satisfied when they have this distance, which...
Is that possibly an expectation of that squared?
That is indeed, yes. Good. Okay, thank you. Okay. And so it will be, so essentially it comes down to each time you pick a clause, how many variables they agree on and how many they disagree on. And basically, if they agree on everything or they disagree on everything, then it will just have probability 1 minus 2 to the minus k minus 1 of being satisfied. So let's get into the k minus 1. Otherwise, there's sort of 4 ways of assigning the variables that will make it things, you know, it not satisfied. So k minus 2. And then we can sort of plot this as a function of gamma. I'm probably out of... Okay, I have 1 minute left. So basically the picture will look something like this. And let's say this is log of expected value of z squared divided by expected value of z. as a function of gamma.
Was a square in the denominator?
No, I don't want a square in the denominator, actually. So at gamma equals 0, then we're looking at identical or solutions. And so then the number of identical solutions is just the total number of solutions, and we'll get log of 1 here. So 1 over n. So it will start off at 0. The derivative will be infinite at that point. And if alpha is small, it will look something like this. So this is alpha less than 2 to the k minus 1 over k log k. But once I go above this, and the maximum will occur in the middle at gamma equals 1/2, corresponding to pairs that are basically independent of each other. And so in this case, the second moment method works. As we increase gamma above this threshold, the picture will start to look like this. We'll get these sort of small local maxima here, and then it will be less than 0 at this point. And the width here will be at most 1 over k. But what this calculation is saying is that if I have a solution here, the expected number of solutions at this distance is exponentially small. So a typical solution will have no solutions at distance, let's say 1 over square root k. But that's, if you have no solutions at a certain distance, that means that you're in a cluster. So this expectation computation plus the sort of planted model or contiguity means that a typical solution will come in a fairly small cluster once we go above this threshold, and it will be the same for coloring and KSAT. This was just the easiest one to do the calculation in, and yeah, so I guess not tomorrow, but the next day we'll sort of look at what the clusters are and how we count them, and yeah, and then, well, we'll almost be done. Anyway, so I'm over time now, so yeah, I should finish off there.